everybody. Welcome to the geometry webinar. Today, I'm very glad to introduce Emilio Lauret from CONICET and Universidad Nacional del Sur in Bahía Blanca, Argentina, who will talk about diameter and Laplace eigenvalue estimates for homogeneous Riemannian manifolds.
Ô, minha senhora, tô morrendo de calor. Filha, eu tô com o microfone.
Okay, thank you very much. Thank you very much for the kind invitation. It's a pleasure to speak in this seminar. Are you hear me, right?
Yes. Sí, sí, se escucha bien.
Okay,
Sí.
Thank you very much to the organizers. I respect very much to all of them, excepting the Argentinian one. And I will talk today about some results in these two articles. The second one is not available in archive yet. I expected to post it during this day in the preparation, but I couldn't. I'm sorry. I hope in the next days will be available. They consider some problem I will talk in a few seconds about, and this consider, the first one consider the Lie group case, and the second one consider the homogeneous case. Okay, so the techniques and everything is very similar. The second one is very similar to the first one, but in some sense, in the homogeneous case, fortunately, the results are more complete than the first one, which only contains partial results. So let me start with just a few simple things. We will consider on a compact connected Riemannian manifold, the Laplace-Beltrami operator, the Laplacian, and we focus only on the spectrum, on each spectrum, okay? Doesn't matter what is the definition of this Laplacian, but because of some properties, is self-adjoint and something else, we have the spectrum is non-negative, real and non-negative. It doesn't contain any accumulation point in the real line. That means that it goes to infinity. It's a sequence. The first eigenvalue is 0. Okay. If you put a constant function and you apply the Laplacian, you always get 0. So 0 is always an eigenvalue because M is connected, assuming connected, the multiplicity of the value 0 is 1, exactly 1. So this lambda 1, the first, usually called the first eigenvalue, is the smallest positive eigenvalue. And it is quite important. It's called the fundamental tone. And Shin-Tung Yao wrote about it the following: while this constant has analytic importance, it also gives strong insight in the geometry of the manifold. In the 70s and 80s, there were many works estimating this number, this eigenvalue. This estimate by Chang in 1977, it was an upper bound, and the rest, which is I read that it's more difficult to estimate by below than by above. The rest are lower bounds. Okay. Most of these estimates work under assumption of a lower bound of the Ricci curvature. The formulas contain sometimes the diameter, the volume, some bounds of these objects, but usually also contains a lower bound of the Ricci curvature. But here we have a theorem by Peter Lee in the 1980 that only assumed it found a universal lower bound on the universe of homogeneous Riemannian manifolds. First, recall that the Riemannian manifold is called homogeneous if the isommetry group acts transitively on it. Okay? Given any 2 points, there is an isometry that takes one to the other one, and geometrically speaking, is that every point looks in the same way. Okay, if you want to compute the curvature, just do it in one point, and in particular, the scalar curvature is a constant function, for instance. Okay. So Peter Lee, under the only assumption, because compact and connected, this assumption is in order to have sense of the problem, but only under the only assumption that the manifold is homogeneous, he found a lower bound for, let's call the functional lambda1 times the diameter squared. Okay, the diameter is, of course, the usual definition, the maximum distance between 2 points, and is compact, so this is a finite number. And the product, this functional lambda1 times the diameter squared, is invariant up to scaling. Okay. So this lower bound does not have a counterpart by above. Okay, there is no any upper bound analog to this. Why? Well, just pick the round sphere. Very simple example. I mean, the lambda1 of the d-dimensional round sphere is just d, the dimension, and the diameter is pi. So we have that this number goes to infinity as d goes to infinity. Okay, so there is no any upper bound like here there is a lower bound. There is no upper bound here. But I guess you are asking yourself, what about if we fix the dimension? Because this is simple examples, the dimension goes to infinity. So let's talk about this problem, which is open. And moreover, very recently, in 2000, the paper published in GAFA in 2018, but in archiving in August 2017, Eldredge, Gordini, and Salof-Coste conjecture the following. You fix a compact connected Lie group G, okay? Compact connected Lie group G. And they claim that there is a real number depending only on G, nothing else than G, such that this functional that we saw in the previous slide is bounded by this C in the following universe for every left invariant metric on G. Okay? So this functional is bounded for the same constant that depends only on the group G, not on the metric, only on the group G for every left invariant metric. Left invariant metric is just pick an inner product on the tangent space of the Lie group at the trivial element. This is the algebra G, and just translate by multiplying by the left this inner product. You get a left invariant metric. Okay, it's a Riemannian, of course, and since the action of G on itself is transitive, is homogeneous. Okay, this the Lie group endowed with a left invariant metric is homogeneous. So it's a particular case of the problem that just discussed. Okay, and the authors obtain they gave evidence on these conjectures because they say that this, I mean, they prove that this is going to be true for G uniformly doubling. And what means uniformly doubling? The following. Check this. This is the ball with respect to the metric G. Center it at any point, because this is homogeneous, doesn't matter what is the point. And here the radius 2r and r. Okay, so the supremum over every r. Of course, for r large, there is no any problem because this quotient is going to be 1 for r large enough. Okay, the problem is r very small. And here the supremum is over every left invariant metric. Okay, you can this factor, you can control this factor independently on the metric G. That's the point. And they prove that there is such a constant if G is uniformly doubling. Okay, this is they say that this is an evidence. The theorem is an evidence for this conjecture because this is, they expect this. They conjecture actually this, that every compactly group is uniformly doubling. And this theorem gives immediately that this is true for every tori, right? Because every left invariant matrix on torus is a flat torus and pretty simple to compute. It depends only on the dimension. That's not a problem. And they prove for SU2. Okay, they really compute this. They estimate or compute explicitly this for SU2 and any left invariant metric on SU2. And they didn't do it but SO3, but I'm pretty sure that it's more or less the same. Okay, and this is these three cases, well, three. Any tori and SU2 and SO3 are the only cases so far known so far that this holds. Okay. And I was very lucky because I started to work in 2017 on given explicit expression for the first eigenvalue of SU2 that is actually the three-dimensional sphere endowed with any left invariant metric on SU2. And it appears this article, so I started to think in this problem at this moment. And I obtained here an explicit expression for the first eigenvalue, for SU2 and SO3 with any left invariant metric. And I apply this explicit expression with some estimate for the diameter, obtaining this. Okay, these are explicit constants. Okay, now that here we improve a little bit the estimate by Peter Lee, but of course Peter Lee's estimate work for every homogeneous manifold, and this is very particular. So it is expected that if you focus, if you restrict the attention of some group, this is going to be better. Okay. So let me.
Oh, Emilio,
yes.
Are these bounds sharp?
I don't remember, but I remember I wrote about this in the paper.
Okay, I can read.
Yes, please. I can read it also. I'm sorry, I will check later. But no, they are not sharp. No, they are not sharp. Okay, let's explain the setting of this talk. It is well known that every compact homogeneous Riemannian space is isometric to one of these four. G is a compact connected group K. K is a closed subgroup, and G is a G-invariant metric. What means a G-invariant metric? More or less the same as before. You fix the inner product on the tangent space of the quotient and just translate by multiplying to the left in some sense that everything fits well. Okay. So every homogeneous Riemannian space is of this form, but our approach will be the opposite. We fix G a compact connectivity group, any compact connectivity group, and we fix K a closed subgroup. It is not necessary that K is connected. And well, we also fix a G invariant inner product on G that always exists because G is compact, and we obtain this reductive decomposition of G as K plus the orthogonal part with respect to this inner product. And then the idea is we fix all these objects and we will try to we will work on the problem just discussing the previous class, but I mean, we want to bound the lambda1 times the diameter squared, restricting our attention to G-invariant matrix on G over K. Okay, we will replace the left invariant matrix on G by this set. Okay, it's pretty standard, this extension. And it is well known that the G-invariant matrix on G over K are in correspondence with the add K invariant inner products on P. Okay, and this subspace, this is not a subalgebra necessarily. Actually, it is usually not a subalgebra. And well, we have a fixed inner product on P, I mean on G, but we restrict to P. And then we know that any other inner product on P will be of this form, okay? We put here 5 and endomorphisms of P, symmetric and positive definite. Any other inner product is of this form. And in order to satisfy the property of being K invariant, we need to ask that 5 is invariant by K. So it commutes with the action of add K, the adjoint action restricted to the group K. Okay, and we will, once phi is fixed in this set, we call G sub 5 the corresponding left invariant matrix. And well, the isotropy representation of this homogeneous space G over K is equivalent to this in Lie theoretical terms is this. Okay, is the restriction of the adjoint of the group G to the subgroup K. Okay, and we restrict to P. Okay, because P was chosen this way is K invariant, add K invariant. Okay, this is the isotropy representation. And each time, this is a convention, each time we write P as a sum of subspaces, we will be assuming that each factor, Pi, is add K invariant and moreover irreducible. Okay, since is add K invariant, it has the structure of K module, and well, we assume that this K module is irreducible. Okay, is there any question so far about the setting?
No.
Okay. So here are the results. We will assume G is simple for simplicity, but there are more general statements. But with this assumption has to be replaced by something that is not very nice. It's pretty technical. So the theorem says that we fix a decomposition as before, of course. Each Pi is sub K invariant and irreducible as a K module. We fix this decomposition, and the theorem is there is a positive constant that depends on G, on K, and also on this decomposition, such that the functional that we wanted to bound is bounded by above, by this number C. For this, not for every G invariant matrix on G over K. For the G invariant matrix over G over K, satisfying coming from 5 satisfying this. What means this is that, let's say, phi preserve this decomposition. What means preserves? That sends Pi to Pi. Okay, and moreover, since these are add K, since Pi is an irreducible K module, and phi commutes with this action, this phi has to be constant on each Pi. Has to be constant, and scalar multiple of the identity. Okay, and because of this, we are dealing the inner product, the G invariant matrix coming from this condition, are those that, when we restrict to any factor pi, it's going to be a scalar. So we are modifying the fixed inner product at the beginning by only in the directions of this pi. Okay. So it is important to know that it's not true that when this decomposition is fixed, it's not true that every G-invariant metric on G over K is of this form. But if you start with the left invariant, with the G-invariant metric, so you start with the 5, there is a decomposition that satisfies this. Okay, it's diagonal with respect to this, to some decomposition. But we started to fix the decomposition. So, as a corollary, in the case that the isotropy representation is multiplicity free, this means that on any decomposition that you do with the isotropy representation, the factors are pairwise non-equivalent. In this case, this decomposition is unique. Is unique, and in particular, every G-invariant metric of G over K is of this form. Okay, so in this case, in the case that the isotropy representation is multiplicity free, we obtain our theorem, our goal, that there is a constant depending only on the homogeneous space, or actually on G and K, and nothing else, such that we obtain a bound, a uniform bound, valid for every G-invariant metric on G over K, under this assumption. And there are many homogeneous spaces satisfying this. For instance, the generalized flat manifolds, many spheres satisfy this, many realizations, not everyone, but many realizations of the spheres satisfy this, and so on. And this case is the opposite to the case when K is trivial. When K is trivial, the Lie group case, we have the homogeneous space G over nothing, G. In this case, the isotropy representation is M times the trivial representation, where M is the dimension of the group or the algebra. Okay, so it's the opposite case in the sense that here there is no any repeated representation. Well, here you have one representation repeated the maximum possible times. Okay, and in this case we obtain the following: you fix an orthonormal basis of G with respect to this fixed inner product, and we obtain that there is C, a positive number, depending, I didn't put, but depending on G, and also on this basis, this is important, such that our functional that we want to bound is bounded by above by this number C for the restricted set of left invariant metrics satisfying that this space is orthogonal, not orthonormal, orthogonal. Okay, it's like we are dilating the fixed inner product only on the direction of these spaces. Okay, and this has dimension n, the same dimension as the Lie group. Okay, one thing I wish to mention, but I didn't write it, is that in the first article I read in archive, there is a more general theorem. Here we said the space of left invariant metrics is M, the same of the dimension, and the order of the space, the model space of left invariant metric is usually M squared, the order. Okay, and we obtain in the first paper a theorem valid for a subset of the same order, not every, but the same order, probably less than the half. Okay, and actually this result belongs to the first article, and these are going to be in the second article. It's not the same. It's not the chronological order. Okay, so let me start with some ideas of the proof, unless there is a question. So we start with the lemma. Remember, this 5 and C here are positive definite symmetric endomorphisms of the subspace P, and it has sense to say that one is less than or equal to this, right? This means that this minus this is semi-positive definite. When this happens, we prove that the diameter satisfies this. Corresponding diameters satisfy this. And the first eigenvalue, the opposite inequality, okay? The first one is not difficult. Actually, it's quite easy because this inequality implies that the metric is less than or equal to this. And then a monotonicity argument implies this inequality between the diameters. But this is quite technical, and I haven't seen in the literature. It's not very difficult, but I haven't seen in the literature. Okay, maybe there is in some part, I don't know. And well, let's try to give some simple estimate. So fix from now on until some point, we will fix an element in this sense. So we fix a G-invariant metric on G over K. And since 5 commutes with the action, K action, the eigenspaces are K invariant. Okay, and this means that what we mentioned in the previous slide, that there is a decomposition. There is a decomposition, of course, in irreducible factors, satisfying that 5 preserve the decomposition, and in particular is an scalar of the identity on each of these subspaces. Okay, and we call, it's going to be very convenient to call this scalar to denote in this way, okay, the square reciprocal of some numbers, and know that they are ordered, okay, the numbers. So our 5 is this one, written in this form. And now that sigma q is the smallest, so the reciprocal is going to be the maximum among these numbers. And then each of these will be less than or equal to this, and take common factor, and we have the identity on P, not on Pi, on P. And more or less the same analogous in this case. This is the largest, so this is the smallest, okay? And then our lemma here implies this, that the diameter, I'm sorry, I am omitting G over K, but I think it is understandable. The diameter corresponding to this metric here is going to be less than or equal to this, right? Because we have this. And by playing with the factors, goes out here and then goes out here. This is not difficult, okay? And more or less the same, but now using this inequality, by using this inequality, we obtain, I'm sorry, here should be less than or equal to, I'm sorry. So here, lambda 1 is less than or equal to this. Again, playing with the scalars, we obtain this. And note that, what is this? G sub identity of P. Well, this is nothing else that our bi-invariant metric that we fixed at the beginning, but restricted to P, right? This is the limit product, which is a normal metric. The normal metric, in principle, the lambda 1 is computable in Lie theoretical terms, and the diameter, I have the hope that it might be computed explicitly. So putting together this, remember there is a typo here, putting together these estimates, we obtain that our functional that we are interested is bounded by this number that we have the hope that is computed, it might be computed explicitly, times this factor. Okay, but this factor now that depends on the G-invariant metric, depends on the G-invariant metric. And moreover, is not bounded by any G-invariant metric, right? Because this is lambda 1, the sigma 1 is the largest, so it is not bounded when you move 5 for every element here. Okay, so it is not. It doesn't help to our problem. So let's consider some more involved estimates. We fix a G-invariant metric of G over K, fixing an element here, and we fix also an index. Take some attention on this index, okay? And we define. Remember, we fix a 5 here, a G-invariant metric, and there is a decomposition that acts by a scalar, and moreover, these scalars are ordered in this way, okay? And then we fix an index, and we define h sub k as the sum of the first k factors, okay? So we call this number, we have 5 written in this way as before, and now we bound this on each factor pi with I greater than k. We didn't do anything, but when I is less than or equal to k, since this number for I less than or equal to k is less than or equal to this number, we bound by this number, okay? And moreover, we take common factor here, and we obtain this, right? And this is not bounded. It's not bounded by above, right? Because k is smaller, so it's in principle is larger this number than this. And let me write in a pretty ugly way. I bound this by putting this infinite symbol. Okay, I'm sorry for that. It's a provoking way to show the following introduction. What means this? It's like we are defining an inner product that it might have some vector have infinite norm, right? This is not possible in a Riemannian metric in an inner product. Well, here is the point. This element is going to define a sub-Riemannian structure. What is a sub-Riemannian manifold? Roughly, it's a triple MDG with M again a differentiable manifold. D is a subbundle. Okay, at each point is a subbundle of the tangent bundle. At each point there is a subspace. Let's say to facilitate the things that the subspace has the dimension does not depend on the point. And G is an inner product on each of these on this bundle. Okay, at each P is an inner product, but in the subspace dp. Okay, not on the whole tangent space, only on dp, and everything moves smoothly. Okay, like in a Riemannian manifold. This is roughly a sub-Riemannian manifold, and another way to say it is, okay, extend this inner product. This inner product is an inner product only on the subspace D sub p point in it. But you might extend to the rest of the tangent space of p by requiring that an element that is not here, a vector that is not here, its norm is going to be infinity. Okay, it's not an inner product, but we can think in this way. And geometrically speaking, it's like if you have a continuous curve that's its tangent vector at some point does not lie here. This curve is going to have infinite length. Okay, it's going to have infinite length, and in geometers want to measure the length of the continuous curve of geodesic and so on. So it's like we have to restrict the attention to horizontal curves. That horizontal curves means that the tangent vector at any point lies in this subspace. Okay, and this has finite length. Okay. So pick any add k invariant subspace of P, for instance this, but pick any one, and you can define a subbundle of the tangent space of G over K. Okay, you define a subspace P. The subspace P is identified with the tangent space of the class of the trivial element. So you translate to the rest of the point. You need that this add k invariant in order that this subspace at every point is well defined. So you have a G-invariant subbundle, and we are going to deal only with G-invariant sub-Riemannian structures on a homogeneous space. Okay. Again, the inner product is going to be defined only in one point, and then you translate. And then this inequality is telling us the following: the diameter of the G-invariant metric induced by this element is less than or equal to, and here this infinite means that the length, the norm of any element, any vector that is not here is going to be infinite, which is more or less the same that we talk here. Okay, so we obtain here the diameter of a sub-Riemannian manifold given by G over K is the manifold, the subbundle is the one defined by this add k invariant subspace, and the metric is this one. Okay, this sigma k is the same as this one. Okay, so we bound this element, the diameter of an arbitrary G invariant metric of a G over K, by something that still depends on 5. Okay, because this HK depends on 5. It's called for every K, but the definition of HK is it depends. This decomposition, remember, it depends on 5. Okay, and again, by playing with these constants, we can take out, and we obtain the following. Remember, here is G naught, is the fixed bi-invariant metric on G, restricted to HK. Okay, so this is more difficult. I wouldn't say this is computable. And I will say something else later, but this number might be infinite. Okay, it might be infinite. I don't want to give the details now, but it might be infinite, so this upper bound would not be very useful. If this is infinite, it doesn't help at all. So this was about the diameter. Now the first eigenvalue of the Laplacian is pretty more involved. Unfortunately, I cannot give the details because we are going to enter in many technicalities about the Laplacian and so on. But let me try to state. The upper bound for lambda 1 is, again, it appears this factor. Here it appears the reciprocal, now appears at the denominator, and no, numerator. And lambda 1, this is the Laplacian of the normal metric, that's not the problem, but restricted to this subspace. What is this? It's the smooth function on G over K that vanishes for every K in this subspace. Check that is the sum of the first K minus 1 factors. Okay, this is less strict than K. Previously it was less than or equal. Now it's strict. Okay. Know that the constant functions are always in these sets, so you always have the eigenvalue 0. But maybe in some cases you don't have anything else than constant function. And in this case, we define this lambda 1 by infinity. And in this case, this is not useful. Okay, an upper bound with infinity here is not useful. Okay, but otherwise we have a well-defined positive eigenvalue lambda 1 here. Okay, again, I don't want to give the details, but I wish to mention a lower bound. This is an upper bound. A lower bound gives more or less the same here, and here the first eigenvalue of the sub-Laplacian. In the same way as a Riemannian manifold has a canonical Laplacian, a sub-Riemannian manifold have it has a sub-Laplace. Okay, but again, I don't want to give more details about this. So let's put together the two bounds. I forgot to mention again. This still depends on phi. This number, as in the diameter case, it depends on phi. This upper bound depends on phi. And so we put together, and we obtain. Remember, here we have sigma k squared, and here we have sigma k squared, the reciprocal. So they cancel, and we obtain this lambda 1 of this times the diameter of this. Both terms depends still on phi. It's something that you don't want, but it holds. Okay. There is something interesting here. Well, first, let's discuss the sub-Riemannian case. Is the diameter of a sub-Riemannian manifold. Here, this is going to be finite. Remember, G over K is compact. This is going to be finite by a theorem by Chow if and only if the subbundle is bracket generating. In general, for arbitrary compact sub-Riemannian manifold, the diameter is going to be, because sometimes you cannot join 2 points by horizontal curves, okay? And then the diameter in this case is infinite. So the diameter is going to be finite if and only if the subbundle is bracket generated. That means that if you bracket 2 elements in this bundle and then you bracket again with something else still in the bundle and take the span of all of these things, you have to get the whole tangent bundle. This is bracket generated, okay? And in our language, in least theoretical terms, remember, we have some bundle induced by this subspace HK, which is the sum of the first K elements, K components in the isotropy decomposition. The bracket generating condition is equivalent that this subspace of G generates as Lie algebra the whole algebra G. Okay, in other way, there is no any proper subalgebra of G containing this. The smallest subalgebra containing this is G. This is the condition, the bracket generating condition in our particular case. Remember, our particular case is some bundle that is G-invariant. So, so we need that the index case satisfy that HK is bracket generating. So we cannot, K cannot be too small. There is some point, the minimum K, such that this is finite. And curiously, something analogous happens in the opposite way. If K is too large, this is infinity, if K is too large. And you can go down until some point. And this point is exactly the same point that this is going to be finite, okay? So there is only one K, and it's the smallest K such that this is bracket generating. The smallest. The previous one, if you put K minus 1 here, this is not bracket generating. This does not generate the whole subalgebra, okay? So there is one point that both are finite. Only one point, only one index K. Okay? Well, the theorem, remember, this is the statement that we saw previous some slides before. Now the proof ends as follows. Before, we always start fixing phi, fixing the G-invariant metric over G over K. Now we fix the decomposition, only the decomposition. We forgot phi. But we prove what we just proved by using the same is there is a constant C1, positive constant, that this functional is bounded by above by C1 for all 5 satisfying some very restrictive property. The property is that on each pi acts by a scalar, and moreover, these scalars are ordered in this way. Okay, the scalar here is the smallest, and then it's increasing. I say the smallest because this is the reciprocal. Okay, it's quite limited in this sense. Once you fix the composition, you can the previous result gives you this property. Okay. So you have to assume that this scalar, these are eigenspaces, and moreover, this is ordered. But the ordered thing is not a problem. But you can do this because you can do the same for any order of these factors. Okay, and you obtain a C tau. Let's call C tau. Let's call more or less the same. So by taking the maximum of this C tau, you have only finitely many ways to permute these components. You conclude that this holds for every 5 satisfying that these are eigenspaces with any scalar. Okay, it doesn't matter how they are ordered, which is the same we mentioned a few minutes ago, is the same as 5 preserve the decomposition. Okay, so the theorem starts with the decomposition fixed, and you consider only those 5 that preserve the decomposition. Well, I have some minutes, so I will finish in 2 or 3 minutes, maybe less. As an application of the previous theorem, we have the following. There is a constant. If you fix the dimension, d, which is going to be the dimension of something, there is a constant depending only on the dimension, nothing else than on the dimension, such that the functional lambda1 times diameter square is bounded by dc, where this x is the underlying differentiable manifold of a compact, simply connected Riemannian symmetric space of real rank 1. What means that x can be a sphere, or a complex projective space, in case this is even, or a quaternionic hyperbolic space, in case this is divisible by 4, or the octonionic, the projective space, the Cayley clay, in case this is 16. Okay? And G is any homogeneous metric on this space. Okay? So you have we are now getting some result that depends on the dimension, but please check that we restrict very much the homogeneous space possible, the underlying differentiable manifold, right? We are considering only spheres, projective space. Okay? And how is the proof of this? Well, for any of the manifolds just mentioned, it is well understood how are the different ways of realize this as a homogeneous space Tuber K. Okay, and there are when you fix the dimension, there are only finitely many ways. Okay, it's a list, not very long, and well, in this list, fortunately, the isotropy representation in each of these rows are multiplicity free. Always, except in 2 cases, okay? Except in 2 cases. For instance, when we realize Sn, the n-dimensional sphere, as SO n plus 1 over SOn, this is a symmetric space. In particular, this is isotropy reducible. Okay? But sometimes it's not multiplicity free, the isotropy representation, and these cases are these 2. Okay, the 3-dimensional sphere and 4n plus 3-dimensional sphere, and these are the ways to realize. Here the isotropy is 3 times the trivial, and here is 3 times the trivial plus the standard representation of SPM. But the point, fortunately, up to isometry, the G-invariant metrics in both cases, the G-invariant metrics, are diagonal with respect to the fixed decomposition. Okay, you fix one particular, well, not very particular, but you fix a particular decomposition of the isotropy representation, and any G-invariant metric is isometric to one, variating only on the direction that this decomposition allows. Okay, and this allows to prove that for this particular realization, you apply the previous theorem and you get the existence of this constant C for this particular case. And I forgot to say that if you fix the dimension and fix one space of dimension D, doesn't matter if it is a sphere or so on, there are only finitely ways to do it. So you have to find this bound C for each of these ways to do it. And then you take the maximum of the different way, and then you have this constant for that holds for every realization. Okay, so you are obtaining this upper bound for every homogeneous metric G on any space of this form of dimension. Okay, well, that's all. Thank you very much.
Thank you.
Okay. Are there any questions? Are there questions?
I have a question.
Okay.
I think Gregorio.
Yeah, it's just one off-topic question, in fact. Suppose, I don't know if it's true, but there is a, we call Sadao iteration scheme with the iterate the green operator. So you take a function, this case would be a function which has perpendicular to the constant, and maybe you have this Sadao iteration, maybe you can reach the first eigenvalue of a homogeneous space. In this case, I don't know how to compute this green operator, but since it's G over K, possibly one can find an expression for this G and see if it's possible to make this this result you compute. I mean, compare one to the other or one metric to the other. See if you can get the minimum of the metric or minimum of the eigenvalue among all of them. But I am just speculating here. I never did this computation. I didn't know your paper.
My answer is I have no idea. I am totally off topic about this. I wish to mention that the tools that I usually use to compute these things are theoretical, quite algebraic.
I see.
It is involved with some Casimir elements in the universal enveloping algebra of the Lie algebra. I just saying things to know that it is pretty only Lie algebra tools. Okay.
I see.
Maybe somebody else can
sure.
answer the question.
Yeah, sure. Thank you, Mr. Emilio.
Okay, sorry.
Grazie.
Enrique?
Yes, so first of all, I don't know if everybody speaks Spanish here. Today is Argentinian National Independence Day, so greetings to our brothers and sisters next door. But Emilio.
Viva Argentina!
Yeah, viva! Patria Libre and the rest of it. But I actually have a mathematical question, Emilio.
Yes.
So let's consider SP2 over SP1 in particular, right? So I've been preparing a question for you all talk long with Andres Moreno. We are going to ask you exactly what about SP2 over SP1, and in the last few lines you spoiled our great question. So what about, so can you please zoom into this? Let's just discuss, say, S7, and so the fact that the G-invariant metrics are diagonal with respect to this composition, how does that nail the matter? How does that close the thing? Can you just explain in detail how it happens here?
I'm not sure if it's a good answer, but it usually doesn't happen that you fix, this is a general fact, you fix the composition of the isotropy representation, and then every metric is isometric to one which is diagonal with respect to this fixed representation. This happens for Spn over Spn minus 1 for every n. And also for S3, and I'm not sure whether there are many more. I have no idea about this, but this is a geometric fact. It is not related to the spectrum or the diameter or something else. It's the form of the moduli space of the G-invariant metric of G over K. This is the most important fact, that it is used for the rest of the things, but it's a more geometric things than the spectral or something else.
So how do you compute the C in this case, just quite explicitly? Is it?
No. In any of these results, the C is explicit, besides in the three-dimensional case. But in this case, it's not explicit. And in these cases, it would be no, even in this particular case, I'm not sure whether it is possible to give an explicit expression of this C, even in this very particular case. But you can, what you obtain by this proof is there is such a thing. I mean, you obtain, where is, I cannot find.
Yeah, it says the maximum of all the,
I don't think it is possible to compute this number explicitly. This is sub-Riemannian metric, and the diameter is quite difficult even for a Riemannian metric. I don't think it's possible to compute explicitly, but it is a number, because when you fix the composition and work for 5 in this very particular way, that each term of the decomposition is an eigenspace, this number does not depend anymore on the metric 5. It depends on the decomposition, but not on the metric 5. And if the decomposition is in some sense unique, it's not unique, but in your case, every metric is isometric to one which is diagonal to this decomposition, then you obtain some number that I don't have any clue about how explicit it is, but at least exists.
Because what we did in some unpublished material is we looked at the invariant, the G-invariant, I mean the SP2 invariant G2 structures on the 7th sphere, and they're pretty well parameterized.
Yes.
So I mean, quite explicitly.
Yes, the metric, yes.
But from the G2 structure, you can compute the metric, and then I was thinking maybe just for SP2 over SP1, we could actually try and compute this.
What do you about what? The first eigenvalue of the Laplacian?
Well, the constant C in this case.
The first eigenvalue of those metrics was computed in a paper in collaboration with Paolo Piccione and Renato Bettiol. We put in archive in last January. And for every homogeneous sphere, it is a formula explicit formula for the first eigenvalue. Okay, an explicit formula, and the main reason is what you mentioned, that the space of G-invariant metrics there are very concrete. Okay, and so the lambda 1, you have the lambda 1 very explicit, and the diameter I'm not sure whether you can give, but it might be possible to give some explicit. Yes, I guess
Cool.
it would be possible, but
It's not like I see Paulo every week. You see, I know actually I do see him every week here. But Paulo, can you please when you give a seminar, can you talk about this? This is really cool. I mean, every geometry seminar has to stop every now and then and talk about Laplacian, right? Otherwise, we're not doing this right. We just have to stop every now and then and discuss the Laplacian again, right? And so if there's a very recent development in a space that we're interested in, it relates to stuff that Andres has been discussing with Jorge, so it has other repercussions. It would be nice to try and everybody should study this. I think I should study this. So Paulo, maybe you can discuss this later in a this result. Thanks.
Yeah,
this is cool.
Okay,
Yeah.
is there any other question or remark?
I'm not sure if everybody agreed that the Laplacian is so important.
They should. They should.
It is. My God.
It is.
It is.
So let's thank Emilio again.
Yeah.